Ever wondered how AI agents can combine multiple technologies and tools to solve complex tasks? Today, I want to show how I was able to use the open source Llama Stack to implement an AI agent that allows me to do retrieval augmented generation against a vector database. And that's just one of its many capabilities. But that's what I'm going to be showcasing because in the past, I had to do a lot of different code and implementation to make something like that happen. And then I also am able to use that vector database in a way that so the agent knows that it exists. It doesn't have to use it. It thinks and knows for a specific type of question whether or not it should actually go out and retrieve that information. And sometimes it will, sometimes it won't, based on the prompt that you give it. But I want to add that extra level of intelligence into my systems without having to get down into those low-level weeds. So I want to tell you a little bit more about the Llama Stack before I do that demonstration, just to give you an idea of all of the different technology that's behind this and all of the different options that you have at your disposal. There's a lot, and this high-level diagram shows a little bit of that. It has things for retrieval augmented generation, as we talked about. So that's the memory piece. Inference, model serving, evaluations to make sure that the answers that it's giving to you are correct, and a lot of these other aspects as well. So this isn't comprehensive, but it gives you some idea. This AI provider, so you'll notice in this diagram, there's different service providers for each of these things. And there's also not listed in here tools. So that's a really powerful component that I want to talk about a bit more. So these tools give a lot of these other components extra power and capability, almost an unlimited amount, if you will, because the options are essentially unlimited. But these service providers, these implementations of the different capabilities above. I know that I have an existing model, for example, that is being hosted on OpenShift, and that uses the VLM runtime. I also wanted an external database for my particular demonstration that I'm going to do, and so I wanted to use this pgVector. So I have a lot of different components that I can choose from and then piece together into a distribution that basically is a Llama server that has all of these capabilities that I can call out to via an SDK. And the one that came closest out of the box to having everything that I wanted was this remote VLM stack, or VLM image. However, it didn't have the persistent pgVector vector database. So I had to create my own distribution. That's where I'm going to come over and take a look and show you the very comprehensive documentation. Where I started was starting a Llama Stack server and then build your own distribution. To do that, I won't go into great detail, but high level, all of those different providers or those API providers can be listed out and put into a build YAML file. There's also a command line tool that kind of does a question and answer session, and then you can pick and choose which ones you want. But I was able to create this. So I have my VLM with pgVector description. So I named it that. It has remote VLM for inference. It also has for the vector IO remote pgVector. And then all I had to do was clone that MetaLlama Git repository, go into the Llama Stack, so it'll be the Llama Stack repository, and then if I do an ls in here, you'll notice I have that build YAML, and then I simply ran this command. That builds me an image. It's already pre-built, and I can do a Docker images now, and you'll see this VLM pgVector. Once that's created, I push that out to an image registry, and I pulled that down. Rather than having all of this run on my local laptop, trying to get the model running and trying to get the agents running and trying to get the vector database running, all of that, trying to do all of that on my local laptop, the perfect tool for that job is OpenShift. So that's why I have my OpenShift running. And in a particular namespace that I named Llama Stack, so under my projects, I can go to Llama Stack. If we take a look at what's running under pods, I have my Llama Stack running and I named it Remote VLLM. It has all of those capabilities, all of the API providers that I want access to so that my SDK can do its job. And then I also have my PostgreSQL database running in that same namespace. And it makes it easy to communicate, but I get off my local laptop and now I can access this environment from anywhere. And then I take advantage of OpenShift AI. So I have in OpenShift AI my deployed models. I have a Llama 3.1 8 billion parameter model that is accessible via this endpoint. And then when I run my project, so when I run my Llama Stack deployment, I can come in, take a look at my deployments, look at my environment variables, and depending on my service providers, I have to populate different environment variables. And in this case, I populate my remote VLLM URL, as well as the inference model that I'm using. And then I don't have to do that in code. Basically that stack, that thing that's running for the Llama Stack just knows these are the things that I can take advantage of. And then I can start referencing models by their ID or vector databases by their ID rather than having to constantly remember in my code to populate certain URLs and all this other extra information when it comes to communicating with those extra services or the tools. Basically, the tools know how to communicate with these other data repositories and other things. Once I have that in place, I can come and take advantage of my workbench. But before I do that, again, I wanted to look a little bit more into the documentation because it's really good documentation. And again, I keep saying these tools, the tools are really powerful. So let's take a look at building AI applications. And let's first come in. There's built-in tools for what I'm going to be showing today, retrieval augmented generation, as well as being able to search the web. So Brave search, Bing search, Tavily search, but then you can, as well as code interpreter. But then there's also this model context protocol tools. And that's from Anthropic. It's a standard that is being used. And out of the box, they have different reference servers for things like Puppeteer, browser automation, and web scraping. That's a pretty cool one. And I'm also interested in graph databases for things like GraphRag. Here, there's a Neo4j. And if we take a look at the documentation, this is what we would do in our SDK to call out to an external tool. And then our agent would be able to register with that and then, based on our prompts, know that it's available and can use that external tool that is a model context protocol tool, as well as this other ability to add custom tools via docstring. So I wanted to show that, but now let's take a look at what I was able to create in terms of retrieval augmented generation and an agent that knows how to go to that extra context before it answers a question. I have in my OpenShift AI, my different data science projects. So again, in my Llama Stack book, I can start experimenting and getting some stuff done really quickly before I turn it into a full-fledged production level application. And what I'm going to execute here is I'm going to communicate with my Llama Stack server via the SDK that I have access to in my Jupyter Notebook. All this line does, what these lines do in this cell, is just give me a list of the models that this Llama Stack has access to. And this URL is not the URL of my model. Rather, I've already put that in. It's instead the URL, if I come and take a look at my routes, of my running Llama Stack. And I just copied that, put it in here. And now if I run this, it will tell me a little bit about what is behind the covers. I have my Llama 3.1 model, and here's what I use for embeddings and a few other things. Let's do a quick, just what everyone is used to. I'm going to use the Llama Stack and the model. I tell it which model ID. It's this one. Hey, you are a helpful assistant. Write me a haiku about coding. Just a simple inference question and answer session, lines of code dance, glitching errors fade away, logic's gentle song. Okay? Now we can get a little bit more comprehensive list using these two lines of all of the different API providers that's behind my runtime, my Llama Stack runtime. Now let's get a little bit more in depth. What we're going to do is create a new vector, register a new vector database, the place where we store this extra context that we want the model to be able to retrieve information about before it answers a question. But again, we don't want to manually write code and go through the steps and say first, go out and get information. We want an agent to be able to intelligently know that this is something it has access to and do that for us. But first we have to get documents in there, and the Llama Stack can help us with that as well. I'm just going to run this. So again, as I mentioned, I've got my vector database running in OpenShift as well. And then I'm able to communicate and look at it just like any other database. So right now there's only 2 tables, or there were 2 tables, but now I just executed that code and now there's 3. So I have my vector store, my demo. But if I do a select on that, there isn't anything yet populated in it, but I have 3 columns: ID, document, and embedding. We're going to go ahead and use a Llama Stack tool to populate with external documents. And those documents can come from any place, or that information can come from anywhere. In this case, I'm using an external HTTPS address. And if I run this, it will pull those down and then put those into the database, as well as create embeddings for that information. But it'll do the work of turning them into chunks and then storing them in an appropriate fashion that makes it easy for our retrieval augmented generation to occur. So let's go ahead and run that. Now, if we come back to our pgadmin and we run this same select statement, a whole bunch of extra information is in there now. Here's the plain text, but then it also created the coordinates, basically the embedding, that makes it easy for our agent to go and find the right information based on the question that you're asking it. It's like a coordinate system. So if we come down and take a look now, we use this Llama Stack SDK to create an agent, and we say, here's your instructions. You are a helpful assistant that will answer my questions, find the appropriate information, and give me a response. We're using a built-in tool, the knowledge search, the RAG knowledge search, and we're giving it the vector DB ID that we just created and populated using the Llama Stack tools. No code other than this code that essentially just calls the SDK, and it's much less work than I'm used to having to do in order to get this level of implementation done. We're going to run this now and essentially ask it how to optimize memory usage in TorchTune, because that was the documentation that we gave it. And it needs to know whether or not, based on this prompt, if it should go out to the vector database to get the extra information. All right, let's run this. It'll take a little while. It has to iterate through a few times until it's confident that it has the response that it wants, and then it will give us our final answer. And we'll be able to take a look at the steps that it took. All right, here we are. Our final answer: to optimize memory usage in TorchTune, you can use the following techniques. And then it lays out step 1, 2, 3, 4, and 5, and that's a pretty good response. And here are the steps that it took. It had an inference step which didn't return any content yet, so instead it did a tool call to get some information about the document, about what you were asking it, and it found these 5 chunks from our document repository. So it knew it didn't have an answer yet. In order to find that answer, it took advantage of the tools and the document repository that it knew about to find an answer. So once it found the answer, it went through a few more iterations to be sure, and then eventually it gets back and does the final step, which is just an inference step, and we have the content populated now. To optimize memory usage in TorchTune, you can use the following techniques. All right, and then once we're done with that, it really makes it easy to use these document repositories as well as clean them up. So what I'm going to do here is just use that same ID. I'm going to clean up now and unregister. And if I come back in here and take a look at the tables, refresh, we'll see that my DB is gone. We only have 2 tables. So that's very powerful. Just a few lines of code in this Jupyter Notebook. And obviously we can take the code that we did in this notebook and turn it into a production level application and deploy it outside of this experimental environment. But what helps greatly is that I'm able to, again, I'm accessing this Jupyter Notebook from a remote location. I can access this stuff anywhere rather than it being on my local laptop, and I don't have to depend on all of these moving parts. Really, the key to this is a combination of the Llama Stack with OpenShift to kind of be lifting up all of those pieces that you saw in the architecture diagram of Llama Stack before, create a retrieval augmented generation system very quickly with just a few lines of code. And not only that, but allow an agent to determine whether or not that retrieval augmented generation needed to happen. And with that, just let me know in the comments below what you would like to see me create and have these AI agents be able to do next time. So I would appreciate that. Just let me know again in the comments below, and I'll see you next time. Thank you very much.